And now we are going to start the next session immediately. Meanwhile, light refreshments are served in the lobby. Please feel free to enjoy. For those who have registered for the Hong Kong Science Museum Guide Tour, please gather outside at 3:45. Meanwhile, I would like to introduce with you, this is me. Have anyone tried this robotic arm to draw yourself? Actually, this is for creating the Chinese traditional ink-style portrait through the AI technology. The project is to broaden the boundaries of the fusion between science and arts. Please feel free to try at the lobby area. And now we will move to the next session. The next session is computer science. We'll be focusing on AI and chips. Next, we are going to have Professor Xie Yun as this session's convener. He is Chair Professor, Hong Kong University of Science and Technology, Fellow, Association for Computing Machinery, Fellow, Institute of Electrical and Electronics Engineers, Fellow, American Association for the Advancement of Science, Member, Program Committee of the Future Science Prize Week 2024. And before Professor Xie introduces the upcoming keynote speakers, I would like to invite Professor Xie to take the photo together with our keynote speakers. May I also invite Professor Onur, MUTLU, Gabriel Low, Professor Wang Yu, and Professor Mayi. Please come to the stage. Thank you very much. Is it better to step forward? Yeah. Okay. And one step to the left, please. Yeah, one is enough. Thank you. We can stand closer. Okay, let's have a look to the center, please. Let's have a look to our official photographer first. 1, 2, 3. 1, 2, 3. 1, 2, 3. Thank you. Thank you so much. May I invite Professor Xie, please proceed to the podium. For the keynote speakers, please be seated. Meanwhile, we can see there are some newcomers. Please feel free to have a seat. And then we are going to have amazing sharing by Professor Xie. Thank you.
Good afternoon, everyone. It's my honor to moderate this section in this beautiful day. And today we have a great list of the speakers for the AI and chip design sections. These two topics right now probably is the hottest topic these days. I would like to extend my welcome to all of you and my gratitude to all the speakers to accept the invitation of the organizers to give the speech over here. Please allow me to introduce the first speaker, Professor Onur MUTLU from ETH, Zurich, who is also a member of Academia of Europe, will deliver his speech on memory-centric computing. Let's welcome Professor Onur MUTLU. Yeah.
Okay, thank you very much for the introduction, and thank you for inviting me to give this talk. It's always good to be here in Hong Kong. I'm going to talk about memory-centric computing. I'm going to take a critical view of how we design computers today and hopefully sow the seeds for designing better, much more efficient, much more higher performance and robust computers for the future. Today, computing is bottlenecked by data. Data is really key for many applications. Machine learning is one example. Genomics is another example. And these applications are growing. These applications require rapid and efficient processing of large amounts of data. And data is increasing. We can generate more data than we can process today, and we need to perform much more sophisticated analysis on more data. And as people dream about new applications will come, and these applications will continue to constrain the power and the capabilities of our devices. This is an example from neural networks. You may have seen this picture. Essentially, memory requirements and compute requirements are growing so that we can make these models better and better. And you can see the numbers. In just 2 years, you have orders of magnitude increases that are needed for both compute and memory requirements. And people are experimenting with interesting things. The person who delivered this talk, Shan Li, is leading a company where you build wafer-scale chips that are of this size, so that they can put compute and memory together. Genomics is another area where we have technologies that can generate a lot of data, a lot more data than we can process. In fact, this is actually a fascinating area. We do a lot of work in this area. There was actually a talk on life sciences session yesterday where people are talking about genomics. I think we need to bridge the gap more between those life sciences and computing so that we can actually process the genomic data in ways that are actually much more useful to humanity going into the future. But this is an area that needs both high compute power and high memory demand. In my opinion, we have actually another responsibility for the future. We're building infrastructure as computer scientists, computer engineers, electrical engineers. We're really building the computing infrastructure for the future. If you think about it, this infrastructure is bigger than any other infrastructure humans have built. Humans have built a lot of infrastructure, but computing actually in scale overcomes all of them. We'll have billions of devices. In fact, we already have a lot. The question is, how do we treat the world? Do we want a world that looks like this, nice, or do we want a world that we cannot even breathe in? This brings us to sustainability issues, energy efficiency issues. I believe, as humans, we're greedy. We want high performance to solve all kinds of problems. We want clear energy efficiency, and we have to do something about sustainability, all at the same time. So to be able to get all of these at the same time, then the question is, are we doing the right thing in the design of computers today? Okay, so basically, today we have a huge problem. We have a data access that in order to process the data, a computing system needs to access the data first. This data is generated somewhere. You take it with sensors, and then you store it in the storage system, and then you move it to the memory system, and then you move it to the caches, and then you move it to the processor so that you can process it. This is actually a very long latency process that requires high bandwidth if you're accessing many pieces of data, and it's also very energy inefficient. So basically, the fact that we're moving data between the processing and data generation and data storage units over and over so that we can actually get something done on that data is causing great energy waste. So we're basically very processor-centric, and as a result, we're causing a lot of energy waste. This also causes great performance loss because this process of moving the data takes time. Unfortunately, maybe fortunately, we recognize that a lot. We actually try to design our systems so that we tolerate that performance loss. We design huge hierarchies for caching, buffering. We design very sophisticated out-of-order execution engines. We design many different levels of prefetchers. We design heavy levels of multi-threading. And all of this is really there to tolerate the latency and performance impact of data movement. And sometimes it works. Many times it doesn't work. Oftentimes it doesn't work perfectly. If you look at some of the caches that we have, their efficiency is around 10 to 20%. If you're lucky, 30 to 40%, meaning most of the data that you cache is useless. You're not going to touch it again. Yet we're building these complex systems. I put this in parentheses because this is kind of the hidden cost of data movement, meaning we're used to designing these complicated systems, and we take it as a given. But this is really bad for sustainability, if you think about it, because you actually produce these huge chips that may not be very efficient. Okay, and this is a vicious cycle, basically. If you want to tolerate the performance loss due to data access, you keep making your systems more complex, and that wastes energy. So we're in this vicious cycle where we keep wasting energy today. And the fundamental problem is we're very processor-centric. All data gets processed in the processor at great system cost, and we kind of ignore memory and communication in the grand scheme of things. Now let's take a look at what a processor looks like. It kind of looks like this today. This is a picture from 2008 when I wrote my first proposal to National Science Foundation in the United States. I used this picture. This picture is kind of similar today also. Essentially what you see here is computation units in the red part. Those are called cores. They could be accelerators also. Everything else, more than 90% of the system, is really dedicated to storing and moving data. Now if you show this picture to a 10-year-old child, maybe that child asks the question, I should not have any problem with data movement. Right? Maybe that child will tell you, yes, you're dedicating almost all of your resources to storing and moving data. You should not have any problem. Unfortunately, the system is still bottlenecked by memory today. Maybe it's because we're doing something wrong fundamentally in our systems. Okay, if you don't like my picture, this is AMD's picture. Gabe can talk to you about that. He's from AMD. Essentially, that green box is processor. That green box is really caches. But there's a lot over there that's not caches, like this is the memory interface. And there's a lot of other stuff for communication with the outside. And we're adding more and more cache. This is beautiful technology, 3D stacking technology. In fact, Gabe's an expert on that topic. 3D stacking technology where you actually put other processors, other things on top of the processor, and you do caching. The question is, are we utilizing our resource in the best way? Okay, if you don't like that picture, this is IBM. If you don't like that, and these are caches. If you don't like that picture, this is something that you maybe in your mobile phone. And this chip is really an SRAM-dominated chip. The rest is really DRAM. And then there's the darkness that many people don't think about, storage. But most of the data is really there. Okay, so we know that actually memory is a bottleneck. So I'm going to go through this relatively quickly. People have known that memory is a bottleneck. For example, this is a paper that was written by Dick Seitz in 1996. After his team designed the fastest alpha processor of its time, he wrote this one-page paper I would recommend everyone to read. He basically says that we designed this beautiful processor. It's capable of finishing one instruction, one alpha instruction, or 4 alpha instructions every clock cycle, which was a very fast clock cycle at the time. Unfortunately, on this important database workload, which we think we designed this processor for, it's finishing one instruction every 4.7 clock cycles. Basically, it's operating at about 5% of its peak efficiency. That's not a good number if it's good engineering, right? And he basically finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, this is data from my own PhD thesis. Together with Intel, we showed that most of the time the processor is waiting for memory. So that was his conclusion also. The processor is waiting for memory most of the time. Recently, Google has repeated this sort of study, and they basically shown that most of the time the processor, a cutting-edge processor, is waiting for memory. It's really finishing instructions only 10 to 20% of the time. Again, it's good to ask the question. We're designing these computers to actually finish instructions, yet they're doing what they're supposed to do only 10 to 20% of the time. Is this a good design? Certainly, it's not a very efficient design. Okay, that was performance. Energy is much worse. This is data that I borrowed from Bill Daly, who was the chief scientist of NVIDIA. The numbers have changed over years, but the orders of magnitude did not change. Essentially, a complicated arithmetic operation, 64-bit double precision floating point operation, is only 20 picojoules according to these numbers. A DRAM, a memory, read or write, access is 16 nanojoules. That's 800x difference. Between 2 to 3 orders of magnitude difference. Basically, does it make sense to move the data, expending a lot of energy, to the processor so that you can do one arithmetic operation and then write back the data over here? Now, this is an optimization problem. You can actually figure out when does it make sense and when it doesn't make sense. The conditions under which it makes sense requires a lot of locality to be present in your workload such that your caching is very effective. In many workloads, this is not the case today. Okay, so that was a complicated arithmetic operation. Let's talk about a little bit simpler arithmetic operation. This is an add, 32-bit integer arithmetic operation. The disparity between a memory access and addition is 6400x. That number is huge. Now, to overcome the energy lost, to amortize the energy cost of accessing data, a piece of data, requires a lot more locality exploitation, which is much harder. Now, we're not even talking about storage. Think about storage. This is memory, main memory. If you think about storage, that's add another 10x over there. We're at 64,000x. We're also not talking about something that's really a big trend today, which is important, I think, making the computation more efficient, like smaller data types. People don't want 32-bit arithmetic. People want 4-bit arithmetic, 3-bit arithmetic, 2-bit arithmetic, 1-bit arithmetic. If you can get away with 1-bit arithmetic, that's much better. Now, the problem is this actually increases the disparity also. So increasingly, the data movement cost is much worse than computation cost. And we have done a lot of studies with Google, for example. On average use cases in mobile workloads, we have found out that more than 60% of the total system energy is spent on data movement. When you're doing web browsing, for example, when you're doing accessing YouTube, when you're doing machine learning inference on your mobile phone. And more recently, we've also repeated the study on machine learning accelerators. Clearly, machine learning accelerators have been used in industry so that you can accelerate many models today, and they have actually enabled us to scale artificial intelligence to larger models. In this case, we're looking at edge machine learning accelerators, and we found out that more than 90% of the total system energy is spent on memory in large machine learning models. Just to give you an example idea, we've studied proprietary machine learning models used at Google, and on large models at the time, LSTMs and transducers, you can see this picture over here. The yellow part and the blue part, they're off-chip interconnects and DRAM. Most of the energy is really spent on off-chip interconnect and DRAM. So actually doing the computation somewhere else, like in memory, reduces that energy, as we will discuss, and can get you much lower energies as shown in this bar, and we will talk about that. Okay, so basically the fundamental problem we have, in my opinion today, is processing of data is performed far away from the data. We need a paradigm shift to enable computation to minimize data movement, compute where it makes sense, as opposed to restricting ourselves to compute where the compute units are currently located. We want to push computation to everywhere where the data resides and where the data may be generated. Essentially, we want to make computing architectures fundamentally more data-centric as opposed to processor-centric, which is what we've been doing so far. And if you look at a computation unit, even an SoC that looks like this, there are a lot of places where you could do computation. We could do computation in the sensors, storage, DRAM. Even within this chip, we're not utilizing the entire chip for computation. Most of that is really memory that's just serving part of the processor. Okay, so we're going to treat memory as an accelerator in the rest of this talk, and we're going to accelerate certain functions on the memory side. We're going to add some specialized computation capability inside the memory. But basically, the broader idea is we could do this anywhere in the system. So we're going to talk about processing inside memory and storage. The processor is going to talk to memory as a somewhat equal partner, accelerator, if you consider that an equal partner. The processor will ask the question, memory, can you execute this function for me? And the memory will say yes or no, and when it's executed, it will return the results. And this is very useful, especially in main memory, because we have huge main memory sizes today. This is very useful inside storage, because we have even huger storage sizes today. Of course, this is not easy, because this requires thinking across the stack. Basically, there are many questions over here. How do you design the compute-capable memory and the controllers? Processors and communication units. How do you design the software and hardware interfaces to enable this? How do you design the system software compilers and languages so that you can actually take advantage of it and enable it to the masses, let's say? And then how do you rethink the algorithm so that it can match your computation capabilities in the memory? And also, how do you rethink the theoretical foundations of computing? So it's really an across-the-stack problem over here. And I'll pick on theory over here a little bit, because if you think about computing theory has been developed to be extremely processor-centric. What we do when we quantify the complexity of algorithms is counting operations. But everything I've shown you so far says that maybe that's not that important, today at least. The operation cost is not that much, but data movement cost is much higher. So maybe we need to really develop a new theory of computation that enables us to deal better with data movement costs and data access costs. And I think that's part of the data-centric computing paradigm. Okay, so that said, you may say, okay, this is an old idea. Why are we thinking about it today? And this is an old idea. People have actually thought about a lot of ideas when they were designing computing systems in 1950s, 40s, 60s. And they've written papers that look like this. This is the earliest that I could find in processing in memory. If you find something else, please let me know. 1960s. This is another beautiful paper by Harold Stone, who has a beautiful textbook on high-performance computer architecture. Essentially, these people have proposed these ideas for different reasons at the time. What is different today? Essentially, I think today we have nowhere to escape. We're having huge problems with memory technology, and we're having a huge demand from application and systems. I've talked about this huge demand, so I'm not going to talk a lot about that again, but designs are squeezed in the middle today. So unfortunately, memory technology scaling is not going well. Even though we have huge memories today, they're becoming less and less robust, meaning we're having errors inside the memory. Rowhammer is another example that I'm not going to talk about today, but we have shown that you could actually induce bit flips in memory by just accessing memory. This should not be happening. This happens because the sizes of the cell that stores data are very small, and the cells are very close to each other. So there's a lot of electrical interference when you access one cell, and another cell gets affected. So you get a bit flip. So essentially, you can get a silent data corruption. You don't want that. We don't want, to build robust systems, we don't want silent data corruption. So how do you solve the problem? Solving the problem is not easy at the device and circuit level. So we actually add a lot more intelligence on the memory side. So we require a lot more intelligence. I'm not going to talk about that in detail, but this is computation in memory, essentially, a form of computation in memory. I've already talked about essentially huge demand from applications and systems. We have huge bottlenecks due to data movement, and we want to improve all metrics at the same time. You don't want to trade off between different metrics. And this means that we need to do something completely different. So I believe we have nowhere to escape. Applications and systems are pushing us to do something different because data movement is a bottleneck. Memory technology is pushing us to do something different because we're hitting the technology scaling limits. So that, and if you want to scale further, we want more intelligence in the memory. And I think we're kind of squeezed in the middle. Now, that's why I believe industry is also moving toward this direction a little bit. But before I go into that, I should mention there are two different types of processing in memory. These are two fundamentally different types, in my opinion. One is processing near memory, the other is processing using memory. Now, if you think about processor or logic and then memory, processing near memory says, put the processor or logic closer and closer and closer, and integrate it nicely with memory as close as possible. This reduces the cost of data movement clearly. This is not that different from what we're doing today. What we're doing today is actually one end of the spectrum. Process far away from memory, but you could get it closer. Industry is adopting this, I think, hopefully, over time. There's still adoption challenges, but there are prototypes that people have been building. Processing using memory is fundamentally different, and I think it's a very good research area going into the future. This is fundamentally harder also. The idea is, you have the processor and then you have memory. Forget about the processor. Just think about the memory, but think about the memory as a computational device. Every memory has some analog operational characteristics that can enable you to do computation. And this analog computation capability is very efficient because you're inside the memory array. You don't move data that much. And then the question is, how do you actually exploit that capability? In the end, I think we need to combine both of these two so that we can get the highest benefits. So this is the landscape today that, from my perspective. So we have 3D stacking technologies where you can put logic underneath memory layers at high performance and high efficiency. And then more recently, people have started developing DRAM chips where near each bank you have a processor. And more recently, large companies like Samsung, SK Hynix, and Alibaba, in fact, Yuan is part of that, have developed DRAM chips that put near bank processors, more like machine learning accelerators on the DRAM chip. So the good news is there's a lot going on in the industry as well, and there are many experimental chips and startups as well. And we have also interfaces that in the industry, like Compute Express Link, that can enable offloading more easily from the processor to somewhere else, including storage. So let me give you some examples of this near memory and using memory computation, and then we're going to conclude. Essentially, 3D stacking technology is an enabler for computation near memory because you can have a logic layer manufactured underneath memory layers with different type of integration technologies. In the ideal case, they're actually integrated very nicely with lots of connections between the logic layer and memory. Now, if you have this logic layer, you can actually do computation in the logic layer. I'll go through very quickly what we have done in the area, at least just one example. If you have this sort of chip, now inside this chip, you can add processors. You can have a lot of parallel processors that are connected to each other. And what we did over here was actually add a partitioned graph. We have graph processing, and we use it as a graph processing accelerator. A graph is partitioned. And if you want to do the computation on a graph node, you actually send the function to the processor that contains the data, as opposed to moving the data between the processors. That's the idea over here. And if you want to scale the system, you need to connect these things, etc. I'm not going to go through this in detail. You can read the paper clearly. But if you do something like this, you get huge performance improvements across many graph processing algorithms. 13x was what we found. Later work actually improved it to closer to 100x. At the same time, you can reduce energy by 8x. That was what we showed in 2015. Later work improved it to also 100x. Imagine we can get 100x improvement in performance as well as efficiency at the same time without even completely specializing. Okay, so that's one example. Now let's talk about processing using memory. There's a lot of interesting work that's going on in the area. I'm going to focus on processing using DRAM. DRAM is a dominant memory technology today, and if we can do something with it, if we can change it so that it can also do computation, we can do a lot. Just a very quick summary, we can do a lot with DRAM. We can do a lot of operations, functionally complete operations, and or not majority. We can do data copying, we can do true random number generation, physical unclonable functions, and if you want to do more complex computation, you can use lookup tables. You can do this mostly at low cost, using analog computation capability. I'm going to give you a couple of quick examples of that. But the basic idea in some of these is really to activate multiple rows. If you activate multiple rows, you can perform computation. And it turns out you can do this even in commodity off-the-shelf DRAM chips that are not designed for this purpose. Okay, and you get significant performance and energy improvements. We're going to look at that. Let me start very simple, with a very simple idea. This is in-memory copy. Today, if you want to copy one page or one piece of data to another piece of data, you have to go through the processor, at least to the memory controller. Basically, you need to bring the data byte by byte to the processor caches, and then you need to write the data byte by byte back over here. Initialization is a special case of copy. Now, if you take this picture and show it to a 10-year-old, maybe the 10-year-old will say, why are you doing this? Why do you have to go through the processor? Why not just do this inside the memory? That's the idea, basically. The idea is very simple. Just do things inside memory when it makes sense to do so. Now, if you do that, it's a low latency, low bandwidth, no cache pollution, and no unwanted data moment. And you can get, essentially, you can reduce the page copy latency by more than an order of magnitude, and page copy energy by almost 2 orders of magnitude if you really optimize it. Now, let me give you the key idea. Again, we're going to exploit the analog operational characteristics of DRAM. Assume that source and destination pages are in this array. You don't need to know too much about DRAM for this, but you activate the source row, which brings the data to the sense amplifiers, which is a buffer inside the DRAM to read the data. And then the idea is to activate the destination row next, such that the data that's in the sense amplifiers reliably gets stored in the destination. Basically, by doing 2 consecutive activations with negligible hardware cost, you can get huge benefits in terms of latency and energy. Okay, so there's more in this I'm not going to talk about. Let's talk about computation. How do you do computation? Again, we're going to look at the structure of DRAM. We're going to go a little bit more in detail. If you concurrently activate 3 rows in DRAM, what happens is you connect 3 of these capacitors to a bit line, and the bit line gets perturbed based on the values in these capacitors. This is basic circuit theory. And then the sense amplifier is supposed to amplify the charge. Now, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. That means you have a bitwise majority function. If you are able to concurrently activate 3 rows, you get the bitwise majority. That's the bitwise majority. And you get bitwise majority, if you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. Basically, you have basic logic functions in DRAM right now. Now, this is very useful. We have shown that you can actually accelerate many applications like databases significantly. I'm not going to go over these results because we have limited time. But I will point out that this is like somewhat theoretical. When we initially wrote the papers, we said that you could do it, and we showed that you could do it in simulation. More recently, we've shown that you can do all of these functions, and even more than we can imagine, in existing DRAM chips. You buy an existing off-the-shelf DRAM chip, you don't modify it, but you modify your memory controller, and your memory controller violates the timing parameters, and by violating the timing parameters, you can actually perform this row copy very reliably. You can perform AND, OR, NOT, NAND, and NOR in real DRAM chips. This is fascinating to me. And we have open sourced our infrastructure. This is PyDRAM. It enables you to actually offload computation in a real program to the memory controller, and the memory controller violates the timing parameters, and you can do the page copy or random number generation. It requires a lot of effort to build this infrastructure, including operating system effort and hardware effort, etc. If you're interested, we're happy to support it. But you get real results on a real processor like this. This is a RISC-V processor that's only at 50 megahertz. That's why the numbers are huge. But that's basically an example. More recently, we've shown that you can actually do the page copy very reliably. Just to summarize, we show that by violating the timing parameters in DRAM, you can copy one row into many other rows with more than 99.98% success rate, almost perfectly. I should remind you that DRAM chips are not designed to support this. We're violating the timing parameters to show that DRAM chips are actually capable of this. You can perform the NOT operation. You can perform AND, NAND, OR, and NOR operations, meaning you're functionally complete. You can build any kind of algorithm on top of this if you know how to do it, of course. Okay, I will very quickly go over this, but basically the reason we can have the NOT operation is because you can connect rows and neighboring subarrays through a NOT gate that already exists. This is a sense amplifier. You activate the source row, and then activate the destination row, and the destination row gets the NOT of A. More generally, by manipulating the bit line voltage, you can express a wide variety of functions. This is one subarray in DRAM, 2 cells, another subarray in DRAM, 2 cells. If you concurrently activate all of them, by circuit principles, what you have is sense amplifier compares the voltage, average voltage over here and average voltage over here. By storing the right values in A and B, manipulating things carefully, which I'm not going to talk about, you can actually get many functions in real DRAM chips. So we tested a bunch of DRAM chips, and we've shown that you can have AND, NAND, OR, and NOR with more than 94% success rate. I believe 94% is actually quite high. I was expecting much lower success rate over here because DRAM chips are not designed for this purpose. There will be no manufacturer that will tell you to do this on their chips. But I think maybe they should investigate this more and more. Okay, there are other things you can do in DRAM. You can actually generate physical unclonable functions. You can generate true random numbers at high throughput, high efficiency. I'm not going to go over that, but you can do this in real DRAM chips today. DRAM chips, again, don't advertise themselves to do this. You can actually do even better true random number generation. We have some works coming up that show that you can do even better true random number generation. These are actually interesting because one of the important things with processing near memory is you don't move the data much. And this is good for security. So if you can securely process your data completely in memory, I believe that will fundamentally improve security as well. Okay. So you can do more. You can do a lot more in flash and other types of memory technologies, which I'm not going to talk about for the rest. But we have a long book chapter where we actually discuss a lot of these, and we're updating it to be much longer right now. Let me quickly talk about adoption. I think adoption is a very important issue. If you want to adopt these ideas, you really need to think across the stack. We need to think about applications, programming, system and security functions, runtime and compilation support, and infrastructures. I believe all can be solved with a change of mindset. I think mindset that we have kind of very processor mindset is limiting us. I believe we can get there step by step. Now let me conclude. I think we want to build fundamentally efficient architectures that requires us to be data-centric. We also want to build fundamentally high-performance architectures. I believe that also requires us to be data-centric. I believe we want fundamentally robust and secure architectures. That also requires us to be data-centric, in my opinion, but I'm not going to put that on the slide yet. I believe we need to minimize the data movement in our systems. So I think I've said a lot of these over here. We want to enable computation capability inside and close to memory. I've given you some examples in this quick time that this can lead to orders of magnitude improvements in both performance and efficiency at the same time. This can enable application and new computing systems, in my opinion. I think genomic systems, for example, is very interesting. This can enable a better understanding of nature, because I think nature fundamentally is not processor-centric, and who knows what else. So I think the future is bright, but we still need to do a lot of hard work in science and engineering to enable this memory-centric computing paradigm. And it's good to think about this thing over here. I don't think we want to completely imitate it, but it's good to take inspiration from this thing. I think this thing is not processor-centric. I'll just say that, because I don't know enough about it, maybe. Okay. So I'll leave you with some references over here. We actually open source a lot of things. If people are interested in this work in this area, you can get a lot of open source stuff online. This is our GitHub over here. And most importantly, I'll acknowledge people who have funded our research. And even more importantly, I'll acknowledge my research group who've done this research. You can learn more about them in our newsletters. And I'd be happy to take questions.
We have time for 1 or 2 questions, right? So anyone have questions, just raise your hand. We have a microphone for you. Or you still digesting, or you want to grab him privately? Any questions? Yeah.
Maybe I can ask one question. So you mentioned that the adoption is very important. You are talking about architecture right now. So what do you see that the importance of the software stack and the ecosystem for this?
Yeah, I mean, that's a great question. Absolutely, it's critically important. Because in the end, you can design any hardware. Hardware design, I think people can be very innovative. But if the hardware can be useless. So there needs to be a software stack built on the hardware. And a lot of the adoption issues that I showed over there are really about software, building the software stack on top of it.
Thank you. Maybe I missed it. Have you showcased some benchmark of the performance on the general calculation like matrix production? Sorry,
could you say?
General matrix production. Sorry. Is there some realization of the general calculation like matrix production?
Matrix?
Yeah.
Multiplication? Yeah, sure. I mean, certainly there are a lot of works that show that you can do multiply and add, multiply and accumulate operations, for example, which is really the basis for matrix multiplication. And also there's analog computing that happens in a lot of the memory devices, like emerging memory technologies, where you can do matrix vector multiplication in the analog domain. So there have been a lot of results that have been shown that processing near memory or processing using memory can greatly improve performance and energy efficiency of matrix operations.
So is there significant improvement in the performance?
Yeah, absolutely. I think you can talk to Yuan, for example. He has a work in ISCA 2016 that talks about that, and many other works. But certainly the improvements are similar, commensurate with whatever I discussed, orders of magnitude improvements in general. The question is, how do you really adopt it in the real life? How do you make it work with the software stack today?
Thank you.
All right. Due to the time constraint, let's thank our speaker again.
Okay.
Yeah.
Thank you.
So let me introduce the next speaker, Dr. Gabriel Le Xiuwei in Chinese. Dr. Lo is AMD Senior Fellow, and he's leading the effort in the AMD research on many interesting projects. And today he will talk about the delivering compute for AI in the post-Moore's world. Thank you. Let's welcome our speaker.
All right, thank you very much. It's an honor to be here this afternoon here in Hong Kong. So today I'm going to be talking about a combination of both AI topics and how to build future chips for them. And so I'll start a little bit with AI, and some of this will build on some of the comments that Professor MUTLU had just made as well. So, of course, right now it's just an amazing time with respect to AI. We're seeing already, I think we're just in the very early stages of AI use cases, And there's already lots of interesting things happening. Right, right now we see kind of a lot of fun stuff in terms of generative models and kind of the large language models and different applications there. We're seeing stuff in gaming, but looking forward, there's also going to be a lot of very serious applications of AI as well. So this can be useful for modeling climate change and a lot of the sustainability types of questions that Professor MUTLU had brought up earlier. There's all kinds of cloud applications. You can think about how we're going to apply AI to healthcare, as at least I know I'm feeling older every day, and all manner of scientific research, right? And so there's many opportunities where AI can have very real impacts on society. And we're going to see a lot of changes in how we do our jobs. AI is going to affect productivity, in pretty much almost every profession. There are some professions maybe more than others. Some areas like legal services, engineering, science, AI is going to be very disruptive in the coming years. It's going to find ways to make us all just, I think, incredibly more productive. There's some areas where maybe it's not as much, but I think even those areas will see some impacts. Even like food service, maybe there'll be AI systems that can help with food safety and quality control. There's a variety of different applications where today we have to spend a lot of specialized human labor, and instead we can actually have AI make people be far more productive. So I think some of this is to be seen. And so the question is, how are we going to enable all of this? Right. So one of the things is that AI, the trends have been growing quite dramatically over the last few years. So we'll take a look at some of these in detail. And so for a while, there was already a substantial growth in the earlier days using some of the kind of prior generation machine learning techniques, convolutional neural networks, a lot of vision processing. And even then, we're seeing sort of this exponential increase in the sizes of these models, doubling every year, right? And just remember, the traditional Moore's law says that silicon capabilities doubles about every 2 years, right? So that's already growing faster than our traditional silicon capabilities was increasing. And then with the advent of the large language models, things just completely took off. Right, and so now we're actually seeing a growth of like 20x per year in the sizes of these large language models. Right, so that means like every year, if I want to be able to build and train the largest model, I have to have 20x more specific weights or parameters inside these models. Right, which means I have to store 20x more data. I have to do at least 20x more computation on that data as well. Right, and that reflects in terms of these models, like how long does it actually take to train these, right? And so it used to be that if you had a reasonable cluster and you had a couple of days, you could sit around and train one of these models. Now you need data center scale computation and weeks, if not months, to train the leading edge machine learning technologies. And this is also just societally challenging too, right? Because not everyone has access to those types of resources, right? And so this has become very challenging overall. Right, and it's not just compute, right? As Professor MUTLU mentioned, energy is a huge factor, right? And I guess the hidden subnote in here is that there's a lot of data movement energy represented by this trend line, right? But again, this is an exponential scale on the y-axis, and we're seeing just tons and tons of energy being used. Where if this continues to increase, we're going to be consuming the entire energy budgets of full countries just to train an AI model, which does not seem like the best use of energy for our society necessarily. All right, so there's some very deep implications of these trends. And on top of that, AI is growing not just in scale, but also diversity. Like, what does it mean to use AI in many different use cases? Right, so this is just a quick example of a few cases of what's a cloud or like edge, which you could think of perhaps like 5G base station or endpoint, which is the devices that you're using every day. And it's just a great variety of different requirements, whether it's from the amount of compute required, the energy, the form factor, et cetera. And so we're seeing not only is it becoming difficult to build AI chips just from a raw scale perspective, but we also have to build many, many different types of solutions as well. Right. And so kind of the net of this is that the demand for AI is just completely outstripping the conventional technology, right? Kind of the bottom line just kind of shows this Moore's law growth curve, right? Where silicon capability doubles every 24 months, right? And then in terms of the compute requirement that, conservatively projecting, it's, just way, way higher than that, right? So how are we going to deliver all of this AI demand to society when the raw silicon is, at best, several orders of magnitude, downhill from there? Right. And that bottom chart there, that bottom line was the ideal case. That's a historical growth for Moore's law. And over the last several years, we've been facing increasing headwinds in terms of trying to scale that technology. Basically, Moore's law is, in some sense, falling apart. Or some people say it's already ended in some ways. Right. This is a graph showing basically how silicon technology has scaled over time. And for a while, the orange line shows the density, right? That you're basically getting this exponential growth. You're getting more devices every generation of silicon. But a couple years ago, we started hitting a little bit of a slowdown there. You see the orange slope falls over a little bit. So we're still getting an exponential increase, but the base of the exponent has reduced, right? So you're not getting as many transistors generation over generation. That's at least partially offset by the blue line in that every generation, the devices, the transistors were still getting more energy efficient. So I was getting more devices, and they're costing me less energy per transistor to operate. But even more recent, in the more recent times, it's happened a little bit before, after the orange curve fell over the knee. We can see that the energy efficiency scaling is also slowing down, and that's very alarming, right? That means in the future we're getting fewer transistors per generation, or fewer additional transistors per generation, and they're also not increasing in efficiency at the same historical rates, right? At the same time, the world wants more AI compute, right? So how are we going to deal with this? And if that wasn't bad enough, there's other challenges. Even though the transistors are getting smaller and smaller, we're getting more and more generation over generation. Not all transistors or not all circuits are created equal. And so, for example, we use those circuits to build analog devices, memory, a lot of the memory, as Professor MUTLU had highlighted, and then some portion of that is the computational logic. And the SRAM, which is used in a lot of the on-chip storage, the density of that is actually slowing down quite a bit. So even though I'm getting more transistors per chip, if I'm using those transistors to build the storage, I'm not actually getting the same density benefits as I used to get. Logic is still doing pretty well, but even that's falling off a little bit of the traditional curves. At the same time, we're getting fewer transistors per generation. It's costing us more, right? One of the kind of the powers of the original formulation of Moore's law was that we get twice as many transistors per generation, but the secret was that at the same cost, roughly speaking, right? So in the old times, building a chip of a certain size costs about the same no matter what you did. And so if I get twice as many transistors, I'm basically paying half the price per transistor every generation, right? So Moore's law was just as much of an economic statement as it was a technical statement. And that is just falling apart all over the place now, right? So I have to wait longer to get my transistors. When I get them, I don't get the same growth that I used to. And then the chart on the right is showing that I'm paying more and more and more over time. Right? So that makes it economically very challenging to build products that can serve these markets in a way where companies can be profitable and not go out of business. At the same time, beyond just building these, I don't have to belabor this too much given the previous talk. The amount of power being spent on memory accesses is just also increasing dramatically, right? And it's one of those things where every joule of energy I spend on moving data is a joule of energy I'm not actually doing computation, right? Moving data doesn't compute anything, right? It doesn't teach you, you don't learn anything from moving a bit from point A to point B. It's a computation where the magic happens. And so every amount of energy that we're not doing on compute is in some sense wasted, right? Wasted opportunity. So, where are we going, in terms of trying to address all of this? So there's been several innovations over the past few years. I'll talk about, some of the recent work that's been done to try to address some of these challenges of scaling silicon systems, and then I'll talk a little bit more about the future too. So, just for the audience, if you're not deeply familiar with silicon manufacturing, basically what happens is you start with a big silicon wafer. Today there's a 300 millimeters in diameter. And on that, you basically, photolithographically print a whole bunch of smaller chips, right? So at a big wafer, you get a whole bunch of little chips. And what you do is you cut them up or you dice them. That's where the word die comes from for the chips, right? So you get some number of chips out of this wafer, right? Once you have these chips, you do some testing to figure out which ones work, which ones don't, because the manufacturing process is non-ideal. Defects do happen, unfortunately. The ones that don't pass the test, well, you basically have to throw those out. Whatever's left over, you take those, you package them up, and those are the processors that now you can sell to into the market as as your regular products. So the problem is that if those chips are really big, every time you have a defect, you have to throw away a large amount of silicon. So an alternative to this that we've been using at AMD is this kind of approach that a lot of people call chiplets, right? Instead of building one giant chip, what you could instead do is build a bunch of smaller chips, right? And with these smaller chips, we can basically get more of them per wafer. Roughly speaking, you end up with about the same total absolute number of defects, right? But each defect is only going to cause you to throw out a much smaller amount of silicon. And so with whatever is left over that's still functioning, we can reassemble these into proper systems, and now we actually have a larger number of chips that we can manufacture, right? And so as we move into these new technologies that are costing more and more, it's really important that we maximize how much useful silicon we can get out of each one of these wafers. And chiplets is a technique that allows us to do that. What's also kind of neat is that once you take a system, a computer chip, and you break it into smaller pieces, you can start specializing, right? So one of the things we did was that we can take our computational cores, the CPU cores, and we build chiplets that have just those cores. That's what we call the CCDs, or the core complex dies. And then for all of the other stuff there, your memory controllers, your PCIe, all this analog stuff that doesn't require the latest and most expensive silicon, well, you can manufacture that on an older technology node. And so our I/O die actually uses a cheaper, more mature silicon technology, and we can mix and match them. Right? When you build a single chip, the whole chip has to be using the same technology throughout. Right? But once you break it up, we have a little bit more options here. Another cool thing is that with traditional silicon manufacturing, we use a photolithographic process, right? And that basically, you have to shine light over a certain section of the silicon wafer, and there's just a limit to how big you can do that. It's called the reticle limit, and it's a little bit more than 800 square millimeters. However, once you start breaking things up and reassembling them, I can actually build more than one, reticle's worth of silicon and reintegrate it, right? So normally, if it's the same type of thing. If I want to build a really big cake, and I have just a cake pan, right? That's limits how big of a cake I normally can make, unless I'm willing to make a whole bunch of smaller pieces and put them all together. And once I do that, I can build an arbitrarily large size cake if I want to, right? So we're kind of doing something similar to that, where we can build much bigger systems than the traditional single chip approach would allow you to. And so this actually comes up with a lot of really interesting cost benefits from it, right? So what we have here is that on the chart, it basically shows what would it cost if you were to build a 64 core system using our technique. That's the blue bars. Or you can build fewer cores. And what we did was, because each of our chiplets has only 8 cores, you can vary the number of those chiplets, right? If I only have 2 chiplets, I have 16 cores. If I have 3, 4, 5 chiplets. And this is really nice because in the past, if I wanted to build a 16-core server for some customers, a 24-core server for some other customers, et cetera, each one of those had to be entirely separate design with different engineering and different manufacturing, different testing. Now I only have to build 2 chips, and I can just vary how many of one of them is, and I can provide a whole a bunch of different products all at once. And then there's a huge cost benefit. The orange or the red bar shows what the cost of that equivalent chip would have been if I built it as a single chip without using this chiplet approach, right? And you see it's substantially more expensive to try to build it as one big thing, right? And again, it's because if I have a defect, I have to throw out a much larger piece of silicon. And there's no red bar on the 64-core side because that one's so big that you wouldn't be able to manufacture it with the traditional monolithic approach. Right, so kind of a couple key insights to take away here. Taking a big system and breaking it into smaller pieces with chiplets, allows you to build larger systems than you traditionally otherwise could. Doing this allows you to mix and match different technologies, which gives you, cost and other benefits. And then by having this kind of modular design approach, we can actually, have almost this Lego building block type of approach where we can, vary and just change how many of these chiplets. We have more chiplets, fewer chiplets, and really quickly and easily deploy a wide variety of different products. Right, and that was kind of, an earlier version of this, but we've been, taking this further and further, right? So we've actually, in our latest generation, we have, 16 of these CPU chiplets coupled with this big I/O die, and so we can, really scale this, and you can build these big, massive systems with what are still fundamentally relatively small and simpler to engineer components, right? If you want to build this as one big traditional chip, it would be just, very, very, very expensive, very difficult to do. Okay, so that helps address kind of the scaling of the silicon part of it, but that's only one piece of the equation, right? Memory is still a huge problem. In traditional servers, many of them are still using, DDR memory. DDR, provides maybe a few hundred gigabytes of bandwidth. But these AI and machine learning problems require terabytes per second of bandwidth, at least using, memory systems, maybe with processing and memory and such that'll change the requirements. But until that becomes a wide-scale technology, we're still stuck with kind of more traditional moving bits from point A to point B. One of the key limitations is basically the package interface, right? The processor only has so many pins, right? It's just like this room has only so many doors, right? If you want to get a lot of people in and out of this room, it'd be better if we had more doors, but there's only, so much space on the walls to do that. And so one of the approaches that, has been advocated and actually, been acted on is called in-package memory, right? If the memory is hard to get to because it's, outside of your package, well, one perhaps naive way is you bring it inside a package instead, right? So you bring everything inside. This gets around the limitations of the pins, the limited number of pins you have in the package, right? Same thing, like we have the drinks outside. If we all wanted to go get drinks all of a sudden, we all have to go through the doors. Another approach is just bring all the drinks into this room, and it'd be a lot easier, a lot faster to access. This is enabled by a variety of different advanced packaging technologies. I'm not going to go into the details here, but there's a lot of just really interesting manufacturing techniques that allow us to mix and match the silicon or different pieces of silicon, processors, and memory all within the same package. One of the problems, though, is just even if I can bring that memory into the package, I still need capacity, right? For example, one of these chips can provide about 2 gigabytes of memory, but the size of these memory, the machine learning models is growing to be much, much larger, so we need as much capacity as possible. And so one of the approaches is to use 3D stacking, right? So instead of having just a single layer of memory, we can actually stack multiple layers on top of each other, right? So now a single stack can give me 16 gigabytes of memory in the same amount of area that original 2 gigabyte took, right? And this should be a very natural approach, right, for everyone living here in Hong Kong, right? It's a very limited land mass. When you don't have enough room, you go and you build vertical instead, right? It's kind of similar here. You're kind of boxed in this package. You don't have enough space to put very many of these chips down, so you have to stack them up. Okay, so it's a real estate solution, right? And so one example of how we put this all together is in our MI200 accelerator, right? So this is basically a GPU compute style accelerator that can do a lot of both HPC as well as AI type of computing. And we basically took what would otherwise be one large GPU, we broke it into 2 separate chips, and then we combined that with 8 separate stacks of this 3D stacked HBM, right? And overall, this provides a lot of compute, a lot of memory capacity, and a lot of memory bandwidth, right? Over it's 3 terabytes per second of memory bandwidth, right? Again, perhaps Professor MUTLU will argue it'd be better to not move that data at all, but at least for now, for the current AI models, this is kind of the approach we have. So, how do we go beyond that, right? So this is already kind of what we're currently have. Well, actually, the MI200 is now about 2 years old, right? So we want to be able to build even larger systems to handle these monstrous large language models. Right, and so one of the challenges is the fact that this package here we've kind of run out of room, right? This is already a big package. You can make it a little bit bigger. The mechanical engineering challenges become, quite difficult, but you might make it a little bit bigger, but you're not going to make it 2x bigger, 4x bigger, 10x bigger to get that, generation over generation capability that you really want to, keep up with the growth of AI. So one of the approaches is, well, we did 3D for memory. We could do 3D for the logic and the computation as well. Right. Actually, this is the same picture that Onur had earlier. Right. So one of the things that the HBM memory, the 3D stack memory, right? We're already putting 8 layers of silicon on top of each other, and that technology though uses a different approach, or a bonding technology called micro bonding. Right. So there's actually these micro solder bumps that provide the electrical connections from one layer of DRAM to the next layer above it. And the spacing of it is roughly in that 40 to 50 microns in terms of the distance from the center of one connection to the next connection, which is enough bandwidth to move the data in and out of that 3D stacked memory. It also has a relatively high thermal resistance, right? Because you have this material that has to fill the gap in between these solder bumps and insulate it and everything else. And so that basically is like having like an extra blanket in between every single layer of your memory, and that becomes potentially thermally challenging if I have something that's consuming a lot of power. Thankfully the DRAM doesn't consume a ton of power, and the power density is not so high, so when the memory manufacturers stack it all up, it stays thermally under control. But if we want to use 3D stacking for our logic, that becomes more challenging. So thankfully there's a new technology called hybrid bonding, which actually provides much denser interconnects. So it's basically instead of having these micro solder bumps in between the layers, the different silicon die are able to basically be placed face to face directly against each other, almost at the atomic level, without any kind of interconnects or any other material in between them. And so that allows us to build really, really dense interconnects. The first generation, it's 9 microns, and so that's already about a 5x improvement compared to 40 to 50 microns, and that's in each dimension, right? So 5x in the x dimension, 5x in y dimension, that's a 25x increase in the interconnect density. And then the thermal properties are also much better because we got rid of that underfill, the material that's in between the layers, since the two die are directly bonded face to face, right? So we use this in this V-cache technology for our processors, where we can stack additional cache on top of our processors to build these giant L3 caches. But we can do that for our other logic and such too. Right, so the MI300 accelerator, is basically this, it starts with this kind of this base, level of silicon, right? This piece of silicon has no transistors, it just has some metal interconnect, right? Just to help hold everything together. On top of that, we can stack all of our 3D, in-package memory. So each of these is a, 8-layer, 8-tall stack of DRAM. Then on top of that, we also integrate these our I/O die, right? So this is basically has some cache. It has all of the memory controllers to the in-package memory. It has all the I/O interfaces to connect it outside the world. And this is implemented in an older technology generation, like I mentioned earlier, because it's not doing the main compute. And then on top of that, we can actually stack all of our compute chiplets too, right? So this is what does all of the AI compute, all the machine learning, matrix multiplication operations, and all the other compute that you need. And so, by going 3D on the logic, we're now able to, continue scaling and pack more silicon into, roughly the same amount of area, right? Now there's a question of how high can you go? You can stack 3 layers, 4 layers. If you look at the skyscrapers around here, that suggests maybe you can go a lot higher, but that does require a lot more innovation, right? To do heating and cooling and electrical distribution in a 100-story skyscraper is very different than what you do in a 1 or 2-story building. And so it does require new engineering, new innovation to keep scaling these things up. What's also really cool is that with this modular type of approach, where we can have these chiplets and we can stack them on top of each other, is that it's also allowed us to build new products pretty rapidly, right? So one of the products we have, we actually take away 2 of these GPU chiplets. Pressing the wrong button. Right, so we take away 2 of these 2 GPU chiplets, and instead we can put our traditional CPU cores there instead, right? So we actually can mix and match these different parts. right? And what's really, really cool is that we didn't have to design a new CPU chiplet. We're actually using the same ones from our CPU server product line. And by just mixing and matching them, now we actually have this heterogeneous compute architecture that has a mix of both CPU and GPU. Right? And this can help some of those data movement type of problems. When I have the CPU working on something and I need to move some of that data to the GPU, instead of having those be in entirely separate packages, I buy a CPU and I have a GPU, now it's just all in one, right? That CPU can communicate directly to the GPU components without having to go long distances. And so there's some really interesting things that you can start doing once you really break down a system into multiple parts, having them have reusable interfaces where I can mix and match things together. So I'm running out of time here, but I think really going in the future, right, that what we're going to see is that as we mix and match all of these silicon components and build these bigger and bigger systems, one of the requirements going forward is that we're going to have to all work together a lot more closely, right? In the past, we can really just build the processor and let the software people do the software stuff, let the manufacturing and platform people do their stuff. But with all these components, there's a lot more interactions, and we're going to see, especially with the evolution of machine learning algorithms, the different data formats, the different algorithms, those are going to drive different architectural requirements. That's going to have different power implications. That's going to have, how we package these things together is going to have thermal cooling, and all of this stuff has to run in a big cycle. And I think that's really going to drive the need for a lot of both our STEM education as well as the research programs that we're driving to really become much more interdisciplinary and a lot broader than they've perhaps had in the past. And so I think it's also it's a fantastic time to be in computer science and computer engineering. There's just so many really interesting and deep research problems for us to all tackle, and I think we all need to tackle them if we're going to do this going forward in a sustainable fashion. So with that, thank you very much.
All right, we have time for a few questions. Yeah.
Dr. Lo, thank you for your interesting talk. I'm Shi Liu, a student of Professor Qi's. And I see that you talked a lot about the chiplets and the hybrid bonding and something like that. And they are very hot topics nowadays. And considering that industry has already integrated those technologies into their products, what do you think would be the opportunities for the academia, especially considering that industry has a lot of experienced engineers and will do much better engineering than the students in academia? Thank you.
Well, so I think you shouldn't assume that the industry engineers are always going to be better. I think there's always new ideas, new perspectives from the students and from professors. What I would say is a very good question. That my response to that is right now, a lot of what we're doing, we as industry, not just AMD, I think it's still very early days, right? The way we've decomposed the system into chiplets, the particular type of architectures we're doing this is just stage one, right? And I think there's a huge amount of opportunity to be more creative, to come up with, because in industry, our job is to deliver products, not necessarily to come up with the most creative solution, right? And as a result, we're not always going to we're not always going to try to build the craziest thing we can think of, right? Because there's real risks, there's schedules, there's engineering costs. And so in many of the things we do, I think they are very innovative, but at the same time, we don't always push the boundaries anywhere close to what they can be done. And so I think there's a lot of really interesting things to be done, both on the architecture side. What are new architectures that can exploit and really take advantage of these different technologies? And then, really kind of talking about my last slide there, what we're building is still very much architectures for the software ecosystem as it exists today. What changes can we make in the way we, everything from the algorithms down to the software and everything else? If you can change that with the hardware at the same time, what could you do? What additional opportunities would that unlock, right? Because there's everything from the algorithms to the fact that the operating system still uses 4 kilobyte pages or whatever, right? There's so many legacy constraints on how we think about architectures that have to be sold today, right? And I think when you unleash yourself from those constraints, the opportunities are immense.
Any other question? Lady first.
Thank you so much. And I'm an undergraduate student from Sun Yat-sen School University, and I have 2 questions to ask. One of it is from the PowerPoint. You mentioned the architecture package co-design that enables flexibility. And well, I was wondering which specific parts that needs to be co-designed in this design, and what advantages can it provide, and what difficulties it may counter, because I think the people that are doing research in computer architecture that's can have little knowledge of the knowledge of packaging, and that's the first question. And my second question is I'm curious about what AMD is doing about facing the problem of the heat management, the serious problem in 3D IC, and is the company willing to choose to face with this difficulty of heat management, or they just choose to avoid this kind of challenge and may choose to bigger chips on bigger silicons like Cerebras do?
Okay. Yeah, so for the question in terms of, the challenges with packaging co-design, right, I think there's kind of 2 sub-questions there. One was, how do you do research when, many computer scientists, don't necessarily know all the details about the packaging, right? And I think that's where, collaboration is incredibly important, right? I'm not a packaging expert either, but I talk to and work with a lot of people who are, and I can give them my problems, or I could give them my ideas, and they can tell me what's wrong, what's broken, and we can work together to figure out if a solution exists, right? And so it's something, and then there's another sub question in terms of like what are some of the problems or opportunities that related to the packaging, right? So some of the challenges are for example in like the power delivery, right? If I have many different chiplets that all have different power requirements, then I have to design a more complex package that can deliver different voltages and whatever is required. I think there's also opportunities where you can perhaps consolidate or amortize some of that stuff, where if there's common needs for some of those chiplets, you may be able to build common infrastructure for them to all share. So the second question was?
Heat management.
The heat management, thank you, Yuan. Yes. Yeah, I should have remembered, it's very warm up here. Yeah, so with the heat management for 3D stacking, it's definitely something that has to be done very carefully. So one of in our products, we've only carefully used 3D in certain specific kind of arrangements where we are able to control the thermals, right? So in the 3D stack cache, what we actually do is we only stack the cache on top of the other cache, because the cache has relatively low power density, right? The CPU cores themselves, where all the compute is happening, that has much higher power density. So on top of that, we only stack passive silicon with no actual power consumption, right? And that just basically acts as a heat conduit to get the heat out of the cores, right? In our MI300, we're stacking logic on logic, but all of the compute is on top where it's closest to the heat sink. And the bottom layer is, again, mostly cache, which is lower power density. There's some data movement and some other infrastructure down there. But we're very carefully adjusting and thinking about what goes where, how much power is consumed by each of these things. And it is something that has to be thought about from the very beginning of the architecture. Right? And that goes back to the need for more co-design, more cooperation with the experts of many different types.
All right. One last question. Okay. Give you a quick question. Okay.
Yeah, thank you very much for this amazing presentation. My name is Ethan Zhang. I'm working for a Chinese entrepreneur organization, and I used to work for Samsung. So I have some understanding of this field. I'll ask you a question from a geopolitical perspective. So, like, how large is the gap between US and China in terms of AI computing and the packaging? Like, how wide is the gap right now? And also, like, how effective is US sanctions on China's, this AI chip, this industry? And do you think China would have a chance to catch up with the US in this term? Thanks.
So, I mean, the short of that is I'm not authorized to speak on those matters, but I think, I think a lot of the answers to those questions are honestly unknown at this point. How effective is it? I don't know. I'm not sure if anyone really knows yet. I think in terms of, I think there's a lot of discussion that is, I think, not productive in terms of, people talking about, the AI race, right? I don't think it's necessarily a race, right? Because in each, field, in each country, in every, potential application of AI, there's very different, requirements and objectives and needs and opportunities, right? And so everyone is going to be running in a different direction, right? There will be some commonalities, but I think a lot of the really, socially transformative AI use cases are going to be different and tailored for kind of every country, every, industry. And so, I don't have a direct answer for, what you asked. If I knew the answer, I probably wouldn't be allowed to say it anyway. But I think, in some sense, I think, it's not just you. It's like the entire, global discussion, I think in some sense is not focused right? I think it's really about, each of these cases, like, how do we get to the AI that makes, that use case more productive, more valuable to society, to the world, right? And I think when you view it that way, it's not so much of a race. I mean, like, each of us are trying to get to a solution for our problem as fast as possible, but my problem is not the same as your problem. It's not the same as Professor Xie's problem, right? And so I think there's a lot more opportunity out there.
All right. Due to time constraint, let's thank our speaker again. The next speaker is Professor Wang Yu. He's from Tsinghua University. He's the department head of the Tsinghua University Electrical Engineering. Let's welcome our speaker.
Thank you very much for the introduction, and I'm honored to be here. And I will talk about, maybe touch a little bit about the last question. Because I am more on the accelerator design, and also touch a little bit about algorithm, and a little bit about the circuit design, and a little bit about the system design. So I will be the bridge from Gabriel to Professor Ma Yi. So this is my contents, and first one is talking about the AI. So this is one of my favorite books because everybody has their own definition about the AI, but I find this one is my favorite. So in this book, Thinking Fast and Slow, people are trying to separate two systems, define two systems. One is system one is the brain fast, automatic and intuitive approach. For example, there is a hot water, I touch it and I bounce my hand back, and this is very fast. So for the system two, that is slower, analytical, and there will be reasoning, right? Because, for example, I'm here because Yuan Xie is my formal advisor. He said, hey, you need to come here. Then I come here. And then I'm thinking about, okay, in this circumstance, how can I speak, especially for the third question, right? So this is from my what I'm thinking. Then I organize my presentation. So this is the system two. You need to think a lot and do it not that fast. So it's thinking fast and slow. So why I'm talking about this is because actually I'm not that not a fully algorithm guy. I'm not doing the theoretical research in the AI era, but I'm more working on the system or the chip design. For the system or chip, there people are working on how to define the F, right? So every system, including your phone and your PC and every system is a y equals fx, right? In the very, very beginning, that is the AI step 1, because in China we call the PC 电脑, right? Electrical brain, right? So that is the AI very beginning. So at that time, you try to break the F because you can expressively written the F into equations. So then it can be break down to addition, multiplication, and moving the data around all the very basic elements. That is the instructions. Then you build up the CPU. So you build up all the CPU for different F. So then people are trying to make the CPU faster and faster. So that is doing fast computation for every F. So this is the first period. That is about maybe when I doing my PhD, that is in 2002, 2007, that could be, people designing the multi-core. That time is AMD and Intel. I think it's 2005, something, AMD and Intel all present their multi-core processor, right? So that time. And for the second step is the perception. There's the system 1 built up. For example, SenseTime, right, is a Hong Kong company, which is founded by Professor Tang Xiaou, who is very famous for the face recognition, right? So for face recognition, you cannot write an equation for or explicitly write a physical equation for the face recognition, but you put X and Y into the system and use a neural nets to fit the F, right? Fit the function. So then you can do the Y equals Fx. So for this figure, you can see that, okay, we can see that the chess board there. So this is finding the content, right? Finding all the objects. So this is the second step that we define it as AI 1.0. So you use different data for different domains and train different models, right? And at that time, it's about beginning, I think, 2011 and 2012 to boost this face recognition or image recognition by the ImageNet and also the voice recognition, boosting voice at the very beginning of 2011, 2012. So I try to work with my students working on how to use FPGA to accelerate the convolution neural network and also the deep neural network and found a company called DeFi Tech. And finally, it was acquired by Xilinx in 2018. So then it becomes AMD, right? Because AMD acquired Xilinx. So I have some connections with Onur, right? So we are all from AMD. Yeah. But after that, that is 2018. So after 2018, I talked with my students, just like the first question, talking about, hey, the industry are designing chips. What should the academia do? Then back to the university, my students are thinking that, okay, now we can do the face recognition and all the fittings by label data, right? What is the next? How can we we can recognize every subject or every object in the one figure, but then can you deduct some of the relationship between this object? So then we think about, okay, at that time there was no, or we don't find out that, okay, transformer is good. We don't know that, but we find out that, okay, there is a knowledge graph and deep learning. Putting them together, maybe you can find relationship between the object and do the cognition thinking. So this is the AI step 3, and for my perspective, now becomes LLM, transformer-based LLM dominated. So I'm more focusing on the computing chips or combining the algorithm and data and the chip together. So we are building up the system. So, and the AI 1.0 and AI 2.0, I've already mentioned. The first one is a point to learning the discriminational task for when you provide some data for one domain and you train the dedicated small models for that domain. But for now, for transformer-based or the LLM part, you try to give all the models, all the data, and learn the general model for the generative task. Take an example is at very beginning, you are trying to use the law data to train a lawyer, right? Now is you try to train a person with all the world data and use some of the law data to turn a person into the lawyer, right? So it's quite a different way. So I think it's very interesting. So now we move to the AI 2.0 part. But this one requires scaling law, right? So they say, hey, if you try to do more compute and have more data and for more parameters, you will have better performance. So but till now, I think it's still true, but maybe in the next 2 years, it's not true, right? And I think Professor Ma毅will talk about it. He's thinking from the algorithm view, but for me, I think still having this scaling law. But I'm from mainland China, right? We don't have that much GPU, right? So thinking about if everyone in China use one big model or foundation model in China at the same time, the total requirement of the computing power is not enough. The gap is about 100 times. So this is the current situation. So because we built up a lot of CPU-based data center, but the GPU or the now accelerator-based is not that much. So and for the future, if AI plus every industry becomes true, then we believe that it will consume a lot of power, right? Maybe at that time, when it's mature, only 20 or 30% is the training cost, and 70 to 80 is the inference cost because everyone is using the models, right? So this is a weird, but it still demands a lot of energy consumptions. So what I'm doing, we are trying to using the co-optimization to lower the power requirement when you do the same task. That is the boosting the energy efficiency. So the energy efficiency, there is a equation there. So before that, people are trying to design the algorithm first, and then design the chips, and then the system. But now, because you need to open the two optimization space, both the algorithm optimization space and the circuit optimization space together, there will be, you will find the best solution. So because AI algorithm is learnable, so you can jointly optimize algorithm and hardware to improve the energy efficiency, maybe 10s or 100x. So I will try to give a little bit detail about this part, because this one is from my last 10 years, maybe from 2012, when we tried to design the system for the AI 1.0, we use this methodology. The thing is, because for AI algorithm, or the neural nets only have two things. One is the connections, right? The other one is each connection has a number. So you have the quantization. So you can use pruning and cut some connections, or using the quantization to make the workload smaller. So this is the first thing. And then if you have a fixed area, then if you can have 4-bit multiplication, then maybe it will be 10 times smaller than a 16-bit or 32-bit multiplication, right? So you will you will improve the peak performance, right, in a fixed area. And also you can try to optimize the memory usage or doing the hardware design and compilation optimization to boost the efficiency. That is, you have 1,000 core, then how can you make 800 of them working together, right? So you lower the workload, boosting the peak performance and boosting the efficiency. Then you can have the best performance for the system. So this is the methodology we provide in 2017. So when I see the LLM, because my students say, hey, there is LLM, should we do this or do something to optimize for LLM? I just ask him, hey, do you see any methodology change from this figure? We find out no. Because still, what you can change is structure, that is the connections, and the data format for each of the connections, right? And you cannot put that large network into a small hardware or into a big hardware because the algorithm becomes larger, right? So there's a huge gap between them. So we try to think, okay, let's do it again. Then we do it again. We find out that, okay, for each of the steps, we can have some of the improvement of the data usage. For example, you can shrink in the models, and you can pruning the data structure. You can use 3-bit or 3.4-bit to have the same performance, and you can designing a specific architecture to be better performance. And you can also, this is for the FPGA, then you can have 20 to 80x improvement. When you put it into silicon, then you can have another 10x. So that is almost 1,000x, right? So you have a lot of space to lower the cost of the LLM. So then we try to do some experiments. So for example, we try to have different cars working together. So this one is relating to the question you asked that in China, how do we do that? Because in China, we don't have that much NVIDIA or AMD cars, so we have to mix them, right? So some of the mix is trying to use NVIDIA and the Chinese car together. But different cars, right? So how to split the task and put it all on the cars and have the similar performance, just like have all the NVIDIA, right? Yeah. So this is what we do, and we have nearly a pretty good utilization, mixing them together. And also, we are trying to also for the serving part. So for serving part, you try to do the batching, scheduling, quantization, and do some algorithm level spec decoding and prefix caching. Then you can also have about 30x, because you need to lower each of the core for one LLM, right? Then people can use LLM whenever they want. Otherwise, you need to pay more. So this is a cloud part, training and the inference. And for the edge part, I think people now are having your own agent soon, maybe this year or next year. Definitely you will have it on your phone or on your AI PC. And this is a very big market. So phones, AI PC, and the cars, they will all have LLM inside. So should we compute this part on the cloud or on the edge? So this is a very interesting question provided for all the chip makers and the application makers. So what we are trying to do to try to optimize the LLM on the existing AI PC chips, for example, Intel one and AMD one, and we can have about 30% or for higher precision FP16, and also for about 10 to 20% for the Int4. So which seems not that much, but thinking about AMD and Intel have a lot of engineers, right? And we only have students, right? So it's a pretty good result from my perspective. And we try to summarize all the chips published or in the industry, and we can try to predict the requirement for the future ones. So this is a summary paper. So if you are interested, you can read offline. And for example, we think that for AI PC requirement, it should be larger than 100 tokens per second for a 7B model, and energy requirement, and also the chip should be less than 20 watts. So that squeeze into the small area, or you don't have a very thicker your PC. So in China, we have a lot of different models, right? So I think in US it's the same, right? But in China, we have different GPUs. So this is not the same in US. US only have NVIDIA and AMD, and the others are very small. But these ones are pretty big and quite similar. Huawei is the biggest, and also Capricorn, Haiguang, and vice versa. So how should we utilize all together? So this is what we are trying to do. So every country has every country's own problem, right? We need to try to utilize our own technology to boost the utilization of all the silicons, right? To have our models trained and all the application or the RM to do the inference. So what we try, I call try to have some of my students back to from Ali and other big companies who say, hey, let's do a small company. And then we try to link the models and the platforms together. So for the last year, we tried to group the people together and founded the small company called Infinigence. And now we have office in Shanghai and Beijing, and also one starting in Hong Kong. So this is for the AI 2.0, the current situation. And I will talk a little bit about the future. I believe Onur has talked a lot about processing memory or near memory computing, but I also agree that this is the biggest problem. Also, the packaging is trying to elevate the distance of the data and the computing. You can see that the very beginning of the AI 1.0, the moving data also consume most of the power consumption, right? So there are different types of processing near or in memory, right? Analog and digital and near memory computing. So I'm not going into detail. I'll take one example is the analog domain PIM, and that is try to use the voltage as the input, and then you program all the matrix, because the neural nets are matrix, right? So the neural nets have their matrix, and all the every elements of the matrix turn into the memories, the conductance, and then you program all the conductance with the matrix elements, and then the vector input vector is the input voltage, and if you get electricity on, then you will have, because Ohm law, right? You will have the current out. Then you do the vector and matrix multiplication very fast, right? So it reduces the data movements and improve the energy efficiency. This is about 10 years ago. Yeah, in 2013, when people told me, hey, this is very interesting. We have built up a memoristic crossbar. Let's build a system. I say, okay. And then we find out that a lot of things need to be done. For example, the device is not ideal, right? And it's analog computing. So now it's digital, right? So you have digital to analog. And if you want to have a larger analog system, then you need to cut the system into small crossbars. And at each of the boundary, you will have to memorize the current, then how to memorize the analog value. So it's very difficult. So you need to turn it into digital and then to memorize, or you will use the inductance or capacitance. So the ADC and DAC, it takes a lot of the energy and power consumption. So from 2013, I put about 10 students and working on the architecture design to show maybe it will have, because they say, hey, you have 1,000 times improvement. But finally, 10x is okay, right? And co-optimization, fault tolerance because it's not ideal, and simulator design because you don't have EDA tools, and ADA and DA optimization because you have the interface problem, and you need to build up some of the test chips, so I do some chip design and security and logic. But of course, we do a lot of research, and we have some very good students graduated and get the best students in Tsinghua, blah, blah, blah. But we don't do the entrepreneur based on that because it's too difficult. Yeah. But still, we are trying to write papers. Right? This one is the recent paper we write with the Professor Huaqiang Wu. And the published in Science is still, we can do something about that. And we see some PIM industry in China and also in US, but it's still trying to develop. And the other one, I think, is the robotics. So in 2018, when I sold my first company, I talked to my student, hey, you can see that for this one, because I'm from EE, yeah, I'm not from computer science. So from EE, we try to, we like the embedded system. So if it's embedded system, you have limited battery. So for a limited battery system, you can only do a few things. So one thing is you boost the energy efficiency. And the other way is to make more agents working together. So in 2018, I tried to have some of my students working on this direction, how to have more robots working together, to have more intelligence. But this one, I find out, okay, that is the extension of the equation y equals fx. Then if after you have the decision of output, you need to interaction with the physical world. So then it's the G, right, GY, and you need to execute. So how to do the execute, right? So this is embodied AI and vice versa. And the other one is different agents have different input or different data. So how to have them collaboratively work together. So that is the different acts. So for this part, we found out that, okay, the paradigm shift is still from equations to data-driven, right? Or combining the equation-based control to the data-driven and the equation-based control together, right? So this is a Fei-Fei's talk, TED Talk, which I find very amazing. So I encourage all the young guys to listen to it. And the data-driven promotes the biological intelligence. And now, maybe you can use it for machine intelligence, especially the collaborative intelligence. So we can find out that, okay, for the lower side, the robotics are trying to learn what the environment looks like and where he is. And upside is how to do the decision. But now, after 2023, you can see that it's a sensing, decision, control integrate together. So people have the humanoid-like robots or others. And I think future is putting all these together to be working together. So this is very interesting direction for the system. So this is my last page. So I think what is very interesting is to support the large LLM to move on. So you need to supply efficient computing power or cost-effective computing power to make it happen. And the other one is we need to build up data infrastructure to push forward the hardware of the robots to work together. Yeah, that's my talk. Thank you so much.
Questions from the audience? Yeah. The lady first.
Thank you for your wonderful presentation, and I have a question. We all know that recently large language models and Sora as the most popular AI application. And my question is, what will be the next popular AI application?
Yeah, actually, I don't think I'm the right person to answer the question, but for what makes me interesting is to having my own assistant. So it's very, very good, because the last time I driving back from one place to another place, and I try to think about a lot of things, and then I cannot write it down. Then I call my secretary on the phone and say, hey, you just get a paper and write down what I told you. And then send me email, right? You're just thinking about that. This can be done in my car by AI, right? This is very, I do think they will happen this year or next year. Yeah, so I'm very excited by this.
Personal co-pilot.
Yes.
Any other questions?
Okay, thank you, Professor. We have do a lot of work about the LLM inference accelerator these years, and but I'm really confused about the token generated speed has beyond the token we read speed. So where is the destination of the inference accelerate and speed up, and why we should focus on the lightweight model anymore? Thank you.
Yeah, actually, I think I don't dig that much into the token generation and the decode part. So for technically, I think the preview part is more computation centric, and for the decode part is more memory incentive. So for a larger model, maybe you can split these two parts, and each one has own architecture from the academia view, right? Because we don't think about cost. And but if you think about future small models and they put together, then you try to reuse all the silicon. Then you need to put them together. So I do think for the future, it still should be defined by the application. Yeah, so now AMD, Intel has their own roadmap, but if there is a big change of the application requirement, I think some of the different architecture will have the chance. So this is my point of view, yeah. Thank you.
All right, let's thank our speaker again.
Yeah, thank you.
Now let me introduce the last speaker, Professor Ma Yi. Last week, Hong Kong U just have a new school of compute and data science, and he's the establisher, he's the founder of that school, and he's the dean of that school. Let's welcome our speaker, Professor Ma Yi.
Thanks, Sharon, for the introduction, and also thanks for having me and inviting me for this exciting event. I learned a lot from just the previous talks, and set a very good stage for my talk. So I'm not a chip guy, so this will not be a chip, but I'm going to make two a little bit daring claims, right? So looking forward, what will happen to, a lot of the chips we have been hearing, right? The chips are making tremendous progress to support AI, to support computing intelligence, okay? So now, I'm going to make two claims, right? First of all, right, memory is computing. Computing is memory. If you truly understand intelligence, there's no separation. There should be no separation in the future, first. Second, I would actually make this claim. I actually made the claim about 3 years ago. I was talking to some of my Berkeley distinguished colleagues who works on chips. They're very busy trying to accelerate the current GPU, CPUs 3 times, 10 times for AI machine learning algorithms. I think that's probably not a topic for faculty at Berkeley, okay? If you look beyond the In fact, actually, I start to believe that the entire digitalization, digital computer, the universal computing, is a huge detour for, at least for intelligence, okay? So in Chinese, we say it's kind of like, all right, 大炮打蚊子, we're building a universal computing for something very, very small, very, very special, okay? In the future, there's be tremendous change, I believe, right? Probably gazillions of. So we have to understand intelligence, right? So, I mean, in the past few years, we're trying to, there's tremendous advances in technology, right? Technology has changed. In Chinese, we call it 技术和发展, right? But in terms of methodology, in terms of 道, 思想方法, I think we have to recap, think hard what we're doing, okay? So now, why we have intelligence? Intelligence is life. Life is intelligence, right? The first pre-trained big model is DNA, right? You pass on knowledge we know about the world, generation after generation. In fact, the way we improve our deep networks these days, big models, the same mechanism. Through trial and error, randomly mutate, and with natural selection. Okay? It's improving, but very costly, very expensive. Right? 就是说物竞天择，适者生存. Right? So now, and if you look at the evolution of life science, actually the life and intelligence evolves together, right? For about 3.6 billion years, we evolved that way, okay? By mutation, random mutation, trial and error. Generations of lives passed on, right? And through DNA, we pass on the knowledge about the world and to learn that way. And about 500 million years ago, right? The individual start to develop brain and eye. That comes to the Cambrian age. 寒武纪, 大爆炸, 生命大爆炸. Because why? Something replaced the role of DNA, our own memory. Individual life start to develop its own memories through perceptions, right? You can adapt to your own environment. You have much better chance of survival as an individual rather than just entirely rely on what's passed on to you by your parents, right? In fact, if you understand, right, the advance of intelligence are like that. It's not relies more and more on your DNA. It's actually relies on less and less on your DNA. The more advanced the form of intelligence, right? After birth, you stay with your parents longer and longer and longer. My kids, which is 60 years old, still with me, right? And yet, so this is actually, scientists know this, right? They call this a phylogenetic. It's actually really about evolving by species. Right? And the ontogenetic is about individual intelligence, embodied intelligence. Right? And of course, life and intelligence continues to evolve, right? Suddenly human appeared, right? In the early days, we start to be able to develop a language. Language actually start to replace the role of DNA. Because not only will allow us to use language to communicate with each other, to pass on our intelligence, knowledge to each other, also allow us to pass on the knowledge from generation to the next. So our kids don't have to spend much time, right, to learn. And about 3,000 years ago, maybe, something magical happened, right? In the past, we have been very much just learn our empirical knowledge from empirical observations. But about 3,000 years ago, something very amazing happened. We start to be able to abstract, develop mathematics notions, right? Logic, causalities, right? Solving problems that differentiate human away from animals. So therefore, just looking at the evolution of the science, right? So when you talk about the word intelligence, it's a very vague word. We have to be very scientific, right? What stage? How do we define this intelligence at different levels? Right? At least if you look at the life involvement, right, there's already at least 4 levels. Right? Early on, we use DNA to pass on knowledge. Then our individuals start to develop knowledge. And then knowledge gets shared by the group, by the communal. And finally, knowledge started to be abstracted. Math, science start to appear. Right? So those are the 4 stages. So where are we at? So this is about 3.6 billion evolution, right, of intelligence and life. It goes together. Now, about just 80 years ago, 1940s, a bunch of scientists are very interested in, can we emulate, using machines to emulate intelligence, right? Started with actually Nobel winner, right? It's called cybernetics. He's the founder of control theory, system theory, right? And his work, actually, cybernetics actually inspired almost all people in that age, right? The first mathematical model for neural network and information theory, Klaus Shannon, how do we encode knowledge, information, and how do we improve our decision? Game theory von Neumann was under his influence. And even Turing, right? Turing machine, von Neumann machine are precisely designed to try to compute, to realize, implement cybernetic systems, right? To emulate, making machines intelligent, right? And of course, in the early days of the machine learning, we learn from the animals, learn from the nature. We should continue to do so, right? How the first model of neural network, even the CNN, right? But it's very much inspired by how neuroscience, how our brains are wired, right? So I believe that in the future, we should also learn, some of even the computing architectures, we should continue to learn from the billions of the structure that the nature has found through billions of years of evolution, right? We don't have to reinvent them from scratch. And this is a sort of recent history of machine learning. Most of people are familiar with, right? And think AI starts in 1956, that's absolutely wrong, okay? The machine intelligence started from 1940s, right? We'll talk about that later, right? And of course, everybody knows the understanding of neural networks actually go up and down. Most of the winters is due to the lack of theory, okay, understanding, right, cause all kinds of problems, right? But we also kind of know the recent history a little bit rosy, a little bit optimistic, right, since 2012, right, and due to the, boosting of data and computation, right, the deep networks can be trained and suddenly applied to language, images, and even all the biological data, right? Proteins and so on. But the evolution, again, look at this evolution, right? I'm not even mentioning early networks, right? Even this evolution, all the networks are designed empirically. Right, in the past 10 years, the architecture evolves very much the same as early days of life, right? Randomly try, something worked, 一将功成万骨枯, right? Out of hundreds of possible networks, one of them survived, right, gets passed on. Everybody make copies, open source, right? It's like that. It's a black box. We don't understand we don't know how to evolve, right? And also those networks does not have intelligence, we'll see that. So, first of all, many people say, what's wrong with this? It's nothing, we don't understand our brain, right? But why do we have to understand what's really going on, right? Not just the scientific curiosity, right? Maybe we understand it, but recently it's getting very, very pressing, right? Because something is very powerful, used everywhere. And history, if it's any lesson, right, tells you, if something's black box, but very, very powerful, influential, people are going to abuse it, are going to manipulate, create fear, right? And to monopoly, to their advantages. That's exactly what's happening. Hence the embargo. If something important, right, I don't want you to have it. So, it's almost a responsibility now in the scientific community. We have to understand what we have done, right? Why do we learn? What is intelligence? What to learn? And how to learn? And how to do it correctly, right? Life spent billions of years to do this. Can we understand the principles behind it? If not, we're just a bunch of blind men to elephants, right? We're going to make outrageous claims, and which are celebrated in the past 10 years. It's very strange, right? If we all are scientific training at all, and we are saying things against common sense, right? A deep network is all you need. Reward is all you need, right? Attention is all you need. Foundation model is all you need, right? If anyone knows a little bit of scientific history, you know this is ridiculous, right?
but somehow those things get celebrated, worshipped. And if this goes on further, this is what will happen. Big models surpass humans, right? They're going to create fears, misleading people, right? Big models are nuclear bombs, virus, wipe people out of the surface. And the people making the same claim are the ones invested most in AI technology, right? Use your common sense. Why they do this? So in this talk, we try to go through this, right? Why do we learn, right? Anyway, in the past years, the technology advanced so fast, we start to ask some very basic questions. Why there's intelligence? Why do we want to learn, right? The fundamental reason why life and intelligence ever existed is because the world is actually not random. It's actually very predictable. We try to use the predictivity to learn to be able to survive better in the environment, right? Hence, I used to say, right, everybody is mutant, including cats and dogs, but they just don't know it, right? They have exactly the same model. They can predict how things fall down, right? They have exactly the same model. They can predict how object falls down. They have the same sense about gravity. The only difference is that they don't write down the same language. They didn't write down in the differential equations. So everybody is trying to build a model, right? So now then the question is, mathematically, what is common behind? If something is predictable, if the world is predictable, in terms of data, in terms of the mathematical question, we want to learn what's predictable. What is that problem? Turns out that this is very universally common, right? If any data, any phenomena, observation are predictable, hence, when you observe enough of them, they always lie on very low dimensional spaces. Like Newton's law, right? If there's low force, particle travels on a straight line. It doesn't appear randomly everywhere next time, right? So that's actually lies on very low dimensional spaces. So make them very, very predictable. And even images, although each image is millions of dimensions, but it's actually all the image on the surface, the actual image lies on very low dimensional spaces. That's a common mathematical problem if you actually know that. For example, right? Because the data is low, if the data lies on low dimensional spaces, allow us to do what? Complete, right? We do this naturally. We also do this for images. Right? It's the same idea, same principle. If data lies on low-dimensional spaces, low-dimensional structure, allow us to do denoising. Hence, we can do this. This is exactly what all the diffusion model is doing. All the generative AI relies on. Right? And also allow us to do correct errors. Because once you know the structure, learn the structure, allows you to do all these things that we do at every second. Our brain is doing that all the time, right? Be able to correct errors, occlusions. Now, therefore, in fact, you can actually summarize mathematically or even scientifically all that is worth learning. The intelligence is trying to learn what is predictable about the world. Mathematics is trying to learn the data, the huge amount, high-dimensional data. What is their low-dimensional structure? Learn that distribution. And then transform them into a very organized way so that I can put in our brain, memorize it, and use it. Right? So this is actually the common problem. Right? Actually, you can formulate this. Now the next question is, how do we do this? Right? If this is objective, then how do we do this? Has anything to do with the deep networks? Has anything to do with this? Right? Turns out that this is a question asked 80 years ago by people like Shannon and Lober Wiener. How do we record, memorize something useful? Once we learn something useful in the world, right, we gain information about the world. Now, how do you measure that, the information? Right? That's actually well, I'll bar details, right? That's a technical. It actually worked out pretty nicely, right? So in order to learn, for example, if I don't know anything about the world, anything could happen. Any blue ball could happen next day, right? I have to record, right? In order to prepare what's the weather tomorrow, if I have nothing, have no prediction, anything could happen here. But if I know that weather is, this is summer, this is winter, right? Only those things could happen. If I know the only thing that could happen are those green balls, I gain information about the world. I save the space, right? I don't have to remember all the blue balls. I only have to remember those green balls. I can have much less storage on my computer to record what is truly needs to be memorized. This is memory, right? This is compression. In fact, learning is about the learned structure of the data through compression, so that you want to be very parsimonious about your space, right? Use limited resource to remember what's most useful, right? And the information actually gave you a code for that, how to record. And it doesn't matter, you use volume, you use the coding length, the storage. This is just a universal measure. How do you gain information? Hence, in fact, all the learning process is trying to learn, although our observation can be noisy, but we try to minimize entropy, to identify the modes in the data, low-dimensional modes, low-dimensional structure in the data. We try to do the denoising, right? So converge on the low-dimensional structures. So for example, my data could be noisy, but I know they come from 2 modes. I try to find those modes through denoising, through compression. They're all anonymous, through reducing the entropy, through reducing the coding length. They're all exactly equivalent, right? In fact, all people have done in the past 10 years with all the deep networks, doesn't matter for recognition and generation, are in this very picture, okay? This very simple picture. What people do with the distribution, except they do this the same idea in millions of thousands of dimensions, not in one dimension, right? For example, for pictures, diffusion models, transformers are doing exactly the same thing, right? How do you process your distribution data? To do denoising, compression, and reducing coding length, reducing the entropy. They're all equivalent, right? For example, classification, right? How do we convert those high-dimensional data into very compact code? We don't know how to do it. Let's fit some very daring people says, well, let's just fit some deep networks, right? As a black box, we fit. Make it fast, right? This is one example. You compress your data. And this is exactly the idea behind the diffusion model, right? All this, diffusion AI, Midjourney, all this generative AI, people celebrate. This is the generative AI age, right? It's actually a very tiny thing for us, right? And you have diffusion AI, Sora. They're actually doing the same thing. Compressed data, right? So a random image compressed to the surface of natural images, right? Exactly the same idea. Remember that one-dimensional example, that's what they do, okay? No mystery, nothing, okay? Now, there's one thing we only clarify what people want to do, right? We learn those low-dimensional structure. We even know how to measure it, how good that representation is. How do we do it? Of course, you can say we don't know how to learn that mapping, right? We fit with that neural networks. What are neural networks doing then? Why any particular neural networks? Turns out you don't need neural networks, right? So once you know what you want to do, for example, you want to minimize the entropy of your data, then you just minimize it, right? Any mathematics tells us we just minimize it. Then how do I minimize something very complicated, right? This is an object function of the feature could be thousands, 10,000, millions of dimensions. How do we do it? We don't know. But what do? At least we can do gradient descent, right? Computing the gradient, pass that, right? So once you do that, something interesting happens, right? So I just do one step at a time, right? The next step is just the current state, follow the gradient, going up and down, 爬山，对不对？可以回吧？ Then you do this step by step. Each step is one descent, right? You repeat this step by step, then change the terminology, step to layers. You get deep networks, okay? So that's exactly, neural networks are exactly nature's way to implement optimization algorithm. Remember, our brain, when you are born, we're not preloaded with PyTorch, okay? If your brain wants to optimize something, it has to realize that iterative optimization algorithm. Your networks are precisely doing that. It's realizing the optimization algorithm for you, okay? It's just physical, carbon-based realization of that PyTorch. So this is, then you actually can derive the network completely, instead of black box, it's just purely white box, because every layer, you know it's doing gradient descent, doing compression, doing denoising, to reducing the entropy. The mathematical, statistical, geometrical interpretation of every layer, every operator, are completely transparent, including every parameter. There's no ambiguity, right? And they even actually start to learn, if you train such neural networks, white box, even they start to appear, some even semantic meanings start to appear, because they are statistically meaningful. They're geometrically meaningful. Hence, potentially, semantically meaningful, right? And you can actually scale this up, right? There's a lot of work on it. You can completely scale this out to billions, trillions of images, right? It just behaves like the, all the empirically based transformers, right? But yet, they are purely mathematically explainable. There's no mystery, complete white box, right? You know exactly what you did to data, right? And this is not all, right? This is very unifying, as I have said, right? All the things you have seen in the past 10 years, right? All the networks, right? Lelet, Alexa, ResNet, ReduNet, Transformer to create, they're all just doing exactly the same thing. They just attention head, rating reduction, minimal description length, score function, they're exactly doing pass-alpha, right? Locally reduce your data to lower dimension, denoising, and reducing the entropy of your data. Everybody is doing exactly the same operation, right? Nothing else. And now you actually can see, at least from both objective and from the architecture, everything are transparent. There's no mystery, right? Instead of in the past, we just have to do a back box input output fitting. All the architecture are empirically designed with trial and error, evolving in exactly early days, right, of life. And now you actually can design based on mathematical objective. This is purely objective, right? This completely has nothing to do. And also, this is actually architecture is from just iterative optimization. And once you train such network, the representation become purely mathematical transparent. Right? You don't get to decide anything. Right? Then, is this enough? Right? So we know where the network is actually, remember, network help you to layer by layer, iteration by iteration, help you to optimize, right? You will find, maybe you iterate enough, you'll find the optimal solution, right? But is the optimal solution the correct solution? No, in generally not, right? You optimize, you hope you get the right solution, not necessarily guaranteed to be correct, right? So hence your memory maybe gets stuck to local minimum, right? Maybe your data is not enough, you optimize too early, right? And how do you know your memory is enough, right? Your solution is right. This model may not be complete. For example, maybe the family of Apple requires 5 dimensions to describe. You only learn 4 of them. There's some app we have never seen, right? You have to change. So hence, you have to use your memory to predict, to regenerate, to predict back to the world. Have I memorized all the apples correctly? The shapes to correct, right? When you have an image, you encode, you remember in your brain. The way to memorize, to test if your memory is right or wrong, you'll be able to resample, get it regenerated. So you can see, in fact, if you look at this principle, right, this is actually this is called autoencoding, right? You have data, you encode to your brain internally, you'll be able to reproduce it. This is autoencoding. Does anyone know why Hinton get a Nobel Prize? What's the network? Boltzmann machine, right? Boltzmann machine is actually after the Helmholtz machine. And Helmholtz machine is after the Hopfield machine, right? Neural network. And both Helmholtz machine and also Boltzmann machine are precisely trying to compute autoencoding. By the way, still very heuristic, okay? But that's already groundbreaking enough. He's trying to realize this for handwritten digits. Okay? Now we know how to do this correctly now. Although all the network before was guessed, right? He guessed how many layers, how many nodes. Now everything here should be homework for students. You know exactly what you do. You do compression, forward, and denoising, diffusion. Both sides are derived from mathematical principles. You don't guess anymore. And you can achieve exactly the same performance as He Kaibing, right, did the math autoencoding. So you use it to do prediction. If you can learn the low-dimension structure, you can complete your signals. Remember the earlier examples, right? And is this enough? Is autoencoding enough? If I can remember something, be able to reproduce it, is this enough? Not enough for nature. Why? In nature, we never learn this way. We don't have this option to check if our recovered data is correct or not, right? Everybody knows the screen is a rectangle, right? Anybody disagree? Have you measured it? Do you ever come up stage and the measure is 90 degrees? The line is straight. The distance ratio is 3 to 4. You never. You don't have the option. When a tiger approaching you, right? You don't ask her to stop. I want to estimate your speed and the position, right? Before I take the next action. Right? All that animal has gone, right? So everything we learn, everything about the world almost entirely from inside our brain. We don't get to train end to end, okay? Nature doesn't have that option. How did they do it? This is exactly what Nobel winner answered the question 80 years ago. You don't do this open loop end to end. Only NVIDIA try to convince you to do open loop end to end, right? Because they want to sell chips to you. Want you to produce also scale AI, want to sell data to you, right? Nature doesn't do that. Nature actually does a closed loop. Learn everything in the brain. So if I want to memorize something, this is my brain memory. My memory may not be right, it may be incorrect. I want to reproduce it, get x hat. X hat may not be the same as x, but I cannot measure the distance in the world, in the physical world. What I do, I map that back to my brain. I imagine, I predict, then I imagine that. Gets everything reproject back to your brain. You compare inside your brain. Say if your prediction is right or wrong. This is called a closed loop, right? And it's called cybernetics, by the way. And these days has a very fancy but a vague name called embodied AI. All right, so embodied AI is 山寨版的, cybernetics. Okay, read the history. And this is the work we actually did with Yang LeCun, right? See, everybody say open loop system, we train a big model, right? But if you retrain it, fine tune it, actually there's a phenomenon called catastrophic forgetting. Once the system gets trained, including the big model, don't think that big model, once you do fine tuning, doesn't forget, actually forget a lot, okay? Right, that's a problem with the open loop system. Once you ask the network to fit new data, all the previous memory get lost very, very fast, right? It's called a catastrophic forgetting. Closed loop system do not forget that fast. They forget very gradually, just like our brain, right? Hence, in the whole world, this is actually with Yang LeCun and work, right? So if you do this, you can learn memory and then incrementally, continuously to learn, and you do not forget that easily. Hence, all memory in the world, all life in the world are closed loop system. Yet, there are people trying to convince everybody in this room, let's do end-to-end, train open loop systems, right? Including Elon Musk. It's actually quite idiotic if you know the history of understanding about intelligence, right? In fact, nature has exactly all nature network system, right? All alive AI system at all scale are closed loop systems. They try to simplify things, organize information, and they have closed loop to correct error, right? Last year, right, 2 years ago, Hinton, his latest single author paper, the title called the forward algorithm. He already admitted, right? First time, he admitted nature doesn't do backpropagation. Nature corrects error by closed loop, right? The forward is doing optimization, although he doesn't say optimizing what. Right? So this is actually what we call, right? Just because network gets larger doesn't justify its AI 2.0. Okay? It's the same methodology, same, brute force method, right? Doesn't change. Open-ended system. It's not what actually, at least Yang LeCun we believe, the AI 2.0, the A stands for autonomous. The system can autonomously learn. Correct, Israel? And also, now, this is has something to do with today's talk, right? Just understand the principles, the objective and principle of intelligence. Doesn't mean you know how to implement it, right? See, everybody, including Ilya, say big model is doing compression. I completely agree with him. The next sentence, he says, oh, it's optimizing Kolmogorov complexity, which is completely wrong, okay? Because it takes human 80 years to realize how to realize compression, how to do compression properly, efficiently, right? The progress in the past 80 years of computers are precisely how to implement things efficiently and scalably, right? For example, the Kolmogorov complexity is completely incomputable, intractable. That's the contribution of Turing and Shannon. Tell us what is computable, what is achievable, okay? But even computable thing may not be affordable. They may be NP hard. You have to study what is a polynomial, right? And when you have billions of parameters to optimize, you cannot even afford any polynomial algorithm. Who is using Newton's optimization algorithm? Newton's algorithm? Nobody. Everybody is gradient descent using backpropagation. Why? That's scalable. Now, why nature doesn't do backpropagation? We cannot afford it. We only have 15 watts. We don't have 10 megawatts, okay? We cannot afford running 10,000 GPUs simultaneously, right? There's still at least 7 to 8 magnitude of efficiency we're looking at. Nature will be able to do this much, much more, right? Completely different from global backpropagation, end-to-end optimization. Even though BP is scalable, nature doesn't have that option, right? The evolution of intelligence is not just about understanding the principles, the mechanisms, but it's also how to realize that efficiently through carbon-based, silicon-based, or maybe quantum-based, who knows? Right. So this is actually an idea, right? In the past 10 years, everybody thinks we should accelerate this darn thing, right? End-to-end. More data, bigger model, right? A lot of people get rich, right? And it's not autonomous. It doesn't correct itself, right? It doesn't know it's right or wrong. It's not a full memory, okay? Recognition and generation still separated. A two segment. Don't celebrate the generative AI, okay? It's just one segment. It's one part of our function of our brain, right? And even a single loop is not enough. Our brain has 250,000 loops. They're massively parallel, massively efficient, right? They're distributed, parallel, and optimizing in loops. Right? That is where the efficiency and robustness come from. Right? Right? We are way to go, right, in terms of architectures, how nature realized the intelligent systems. Right? So then what is intelligence? There's a profound confusion in the past decades, right, despite the technological advance. People confuse two related but fundamentally different things. One is called knowledge, one is called intelligence, right? So intelligence actually is one has a mechanism for self-correcting and self-improving for existing knowledge, right? Any system, no matter how big, if cannot self-correct itself, does not have intelligence, okay? Just a memory, right? So if you ask yourself, GPT-4 or new baby, which one has intelligence, which one have knowledge? The answer is obvious. GPT has the knowledge, but not intelligence, right? To some people, this may sound absurd, right? Think about hard, right? The baby has intelligence. Why? It may not have knowledge yet, but it may grow to be a next Einstein, be able to add to the existing knowledge, discover something new about the world, right? So for people to remember, right? Knowledge is actually the integral of intelligence. Intelligence is a derivative of knowledge. Very simple. Right? So now, here's another thing, right? Just young kids, right? So everybody, a big lesson, right? 读历史啊 ，read history. Okay, don't get your history from 自媒体 Wikipedia. All right, go to the original text. Right? This everybody celebrate, right? There's no doubt. Everybody celebrated the past 10 years artificial intelligence, right? Well, this is a little bit, there's a history 给我们开了一个很有趣的玩笑 okay? This artificial intelligence is not that artificial intelligence. Everybody quote AI, right? After this talk, I hope everybody in this room don't make this mistake anymore, okay? Read the proposal. Attempt will be made to find out how to make machines use language, form abstraction and concepts, solve kinds of problems now reserved for humans and improve themselves. The precisely try to distinguish what is different from the intelligence different from animals and human. Causal, logic, abstraction, symbol. Right? Those are the bunch of young researchers. They try to precisely not to do cybernetics. Right? The 40s program is precisely about animal intelligence, signal processing, memory, prediction, error correction, control and game, reinforcement learning. Right? Sounds familiar? So look at what we are doing in the past 10 years, right? Object recognition, image generation, text generation, compression, reinforcement learning. Is this similar to what the 1956 program, language, abstraction, logic, inference, causality, problem solving? No. So past 10 years, we're at here. We are very much here. It's a renaissance not about AI. It's a renaissance of cybernetics. Right? So therefore, if you understand this history a little bit better, right? So machine intelligence has, I think, that it's the 3 phases, right? Even this coincides with the evolution of life and intelligence, right? Early on, pre-trained big models to memorize knowledge. Sounds familiar? DNA is doing that. Even the methodology we evolve is similar, right? We mutate and get selected which one survive. Then open source it. Then everybody copy. Yeah. But there's no intelligence. Individual doesn't have intelligence. Species and the environment together has intelligence. Okay? The closed loop system. Then individuals start to develop brain, memory, and eyes, senses. They start to form their own memory. Learn autonomously, individual, right? That's animal, right? We are very much trying to cross here. In terms of human brain, logic, abstraction, reasoning, we haven't started yet. Okay, so I have 2 PhD students at Berkeley. They don't do anything, they do one thing. Every time there's a big model coming out, they test if the model understands numbers. The simplest abstraction, the simplest symbol, natural numbers, not even rational, right? Not even 复数, okay? Complex number, forget about it, right? Real number, forget about it. Just natural number. Do they know which one? So after GPT 401, right, came out, 5 seconds later, my student told me 3.911 is still bigger than 3.9, okay? I post on Twitter, everybody yelled at me, right? But Yang Lekun retweeted it. Everybody yelled at him, right? So, and then I screen captured it, posted it, crowd down a little bit. People start thinking. And in the afternoon, they fixed it, right? If you ask the 9.1, they actually fixed it. But if you ask it in a slightly different way, still, 3.11 is still bigger than 3.9, okay? And one of the game, my kids, 13 years old kid, although there's some MIT professor thinks the big model has become sentient, right? Conscious, right? My 13 years old kid, my younger son, his favorite game these days is to trick all the big model to believe 3 plus 3 equal to 5. Okay? Try. You have a very high chance to succeed. Okay, I can tell you. Okay? That's his favorite game. If it does not even pass the Turing test of 13-year-old, what we're celebrating? Okay, yes, everybody, there's a lot of very usefulness, but as a scientist, as a researcher, there's a lot of things we should become more sober about it. Right? So now I think we're at the stage we understand the objective, at least for low-level intelligence, at a memory level, computing level, right? We have good understanding of the objective. We understand the reason, the role of deep networks. We can actually improve them tremendously now. We no longer live in the China era age. I'm pretty sure about that. All my students are designing new architecture completely based on guidelines. You don't have to guess, right? You can use optimization principles to improve your architecture design, right? You no longer work in the dark. But also, right, because we understand how limited we have done in the past 10 years, right? And become even more optimistic how wonderful, right, the future bright will be for younger students. We barely scratch the surface about understanding intelligent systems. And not alone, building efficient system, complete, correct system to realize them. We only build a fraction of our memory systems. Recognition and generation separated. 记忆的碎片. Now it's time to integrate, build a complete system. And the system can self-improve, self-learn, build their own memory, truly has intelligence. Maybe after we've done that, one of the people, genius in this room, start to figure out what happened. The human brain start to abstract, start to form symbols, start to discover logic, start to discover causal relationships, start to do inferences, to solve mathematical problems. That's my talk. Thanks.
Wonderful talk. After Professor Ma's presentation, I felt that we have hope that we don't need that many GPUs anymore, right? Due to time constraint, maybe two questions. One from the back. Yeah.
Dear Professor Ma Yi, thank you for your excellent presentation. I have a question I'd like to ask. Since deep learning frameworks can be mathematically white boxed, could a learning structure based on mathematics be proposed that is more efficient than deep learning, such as a closed loop system you proposed?
So there are two separate questions, separate answers, right? So yes, even just for open loop, designing the optimized architecture, deep network architecture, now you know what each layer is doing. You know what the objective is trying to optimize. You can actually do a lot of changes, right? For example, there will be at least two architecture. See, guys, if you look at it in the past, all the architecture were discovered independent by different groups, right? That already says something. There's no principle. There's no design. There's no guideline. Everybody just try. Someone got lucky, right? It's like early days, right? Gets natural selection. Now, second, now you know what it's doing now. Now, actually, at least in just the past year, my group already had the several architectures coming out. You'll see. They're much more efficient. You can actually prove, for example, based on the transformer, turns out you don't need the MLP. Turns out the even computing correlations, the attention can be linear complexity. It doesn't have to be quadratic, right? Because you know what the operation is doing. Right? Even the white box architecture right now we derive is based on the most naive basic optimization you can ever imagine. Okay? There are 300 years of history about how to design better optimization algorithm. There are 10 different versions at least, right? Even for gradient descent, there's many, many different versions. We have never even tried them yet. So barely started, even design better architecture. Second, once you know the segment, how to put into a system, a closed loop system, do we solve them, still optimize them end to end, or we can do layer wise? Nature doesn't definitely not do global, right? Now how our memory optimize our recognition paths and our generation paths, we have no clue. We have some ideas, but in terms of implementation, has not started yet, okay? Including the closed loop system we did with Yang Kun, still we're doing still a little bit brute force global optimization. But we see the benefits of that already. It becomes more consistent. And also, it does not forget, and so on and so forth. It can support continuous incremental learning. But in terms of efficiency, it's far. We have not found the right answer yet. So what are the correct optimization strategy for the closed loop system? We don't know. But at least you can see from this, and once you're understanding the neural network, what it's doing in the forward pass is optimizing. You actually can compute those parameters in the forward pass. You don't have to solve. You don't have to optimize everything from scratch to do backpropagation. So, which is already a huge save, right? You can optimize the network both forward and backward pass. The theory already gave you that option. That has never been an option before, right? So about 15 years ago, my group wrote a paper called the PCA network. It's completely computed forward fashion, right? It actually reached the state of art on face recognition, digital recognition, but nobody believed it. It's only have 2 layers, simplest networks. See, there's a lot of simplification can be done, guys, right? That's why, nature is all about the parsimony. Remember the quote I did in the beginning from Einstein, right? Science, intelligence are following exactly the same principle. Try to make everything as simple as possible, but not any simpler. So your memory just serves you right for the prediction, right? So that's actually, we are still a long way to go to emulating the kind of intelligent mechanism that nature, even at the animal level, we're a long way to go, let alone human, the abstract intelligence, the true artificial intelligence, okay? The word, adjective, artificial, find out what that adjective is trying to define correctly, okay? Don't take that from 自媒体, right? Even from Google or OpenAI's, reports, okay? Intelligence should be really truly defined clearly as a scientific and a mathematical or even a computational subject. And yes, it can become a very rigorous, no longer a empirical study or purely technological subject. I think now should become a scientific and a mathematical subject from now on, yeah.
All right, let's take, I think that if you have more questions, we can ask offline. I think that's conclude this afternoon section. And thank everyone to attend this section and also thank our speakers. All right, thank you.
May I now invite Professor Xia to proceed to the podium to give a summary of this section. Yeah, could you, please. May I invite Professor Xia to give us a summary for this section? Thank you.
Yeah, so, all right. So actually, I'm very glad that everyone stayed here for these four wonderful speeches, actually from US, from Europe, from mainland China, and from Hong Kong, and also from different subjects, from accelerated design, from architecture, and also the last one from Professor Ma Yi on the algorithm itself. And I think Professor Ma Yi's talk is very inspiring. It's actually give us computer architecture guys, like there's a different way to do AI. And I think that I checked with the organization group. They said that we have about 200 audience locally and almost 1 million audience online. So it's very impressive, all right? Thank everyone for attending this section. Let's thank the speaker again and also thank all the audience. Thank you.
Thank you so much, and please be seated. Thank you very much. Ladies and gentlemen, it's the finale of today's symposium. Once again, thank you so much for joining 2024 Future Science Prize Week and the Science Symposium. I hope you enjoyed as much as I did. For those who will return to the hotel, please gather in front of the entrance because we have arranged a shuttle bus for you. See you around at the Future Science Prize Week. Thank you very much.